Continuing with the Intro to Convolutions handout and looking at more examples of convolutions. I'm not going to do this one in exquisite or excruciating detail. I'll leave that for the written solutions that I'll post soon. But we're going to do the step function that turns on a b, and we're going to convolve it with the unit area rectangular pulse, that's what the little r means, remember, with width a. And the claim is that's a trailing moving average of this function. We're still having this purposely asymmetrical point of view where this is the function to be manipulated and this is the thing that manipulates it. And we'll talk a bit about how we can exchange that. But it totally works right now. Well, let's just think what it should do. If you're taking a trailing moving average, when the function has always been 0 and nothing else, then you're just going to get 0. At b, the window is going to start to see part of the increase here. But for example, if you're at this point here, before you get to b plus a, your window goes back to here, it's going to have an average of some zeros and some ones. Remember, this is the value of 1. Okay, so it's gradually going to increase. Now at b plus a, right here, b plus a, then the window goes exactly back to where the cutoff was, where the step was, and you're going to get an average of 1 from then on. So it should be a piecewise continuous ramp function, essentially. It's really good, and again, I'll work it out in detail in the work solutions, in the written solutions PDF, how that works out of the definition. And it's just 3 cases, this case, this case, this case, and doing the integrals carefully. Okay, but qualitatively, what do we notice? Once again, convolving with this window function, even though it's discontinuous and this is discontinuous, we got a continuous result. It's an aspect of integration being inherently a smoothing procedure. And so we've gone from something that's discontinuous to continuous. Now, it's not differentiable. Let's not ask too much. Okay, so I really like that example as a reasonably simple example of the idea of convolution as a moving average. Let's do one. Oh yeah, let's see. For D, we're sneaking up on the fact that this is really a commutative operation. And if you write this down, a little manipulation, especially a change of variables, is super useful. You discover that this is exactly the same thing. And that's an extremely general fact. It's going to be commutative in general. But it's kind of nice to sneak up on that, I think, to get it in the concrete cases first. Okay, now here's a more complicated one. Definitely not going to do all the details for you on video because it would be extremely tedious. Okay, f of t, I write it as a sum of like linear functions and step functions and things like that. It's the punchline is that it starts at b. So again, I highly recommend pausing and looking at the PDF and doing it yourself. It goes from it starts at b, goes up in a triangle and then down, back in a triangle, and these are both slope 1, so that the maximum is also b. Okay, so it's a finite triangular pulse like this. Okay, so there's f, and then again, just to be simple, we're going to convolve it with something that's pretty simple and benign. Again, the R0a, and we're going to look at the convolution of those two guys. Well, let's track it through. Actually, let me go ahead and do it. I'll do it on the same graph here. Okay, so t's going this way. So I'm just going to imagine this window moving across. Until we get to b, nothing's going to happen. Okay. Now, as we go from b to b plus a, let's say that's about here. Okay, it's going to gradually start seeing the linear increase. What that does is it makes a quadratic increase. And then for a little while, until we get to 2b, it's just going to track the linear behavior, but it's going to be delayed from that. Because when you track a linear function, and I look at the window, let's say the window is from here to here, I'm going to be looking at the average of that linear function, and it's going to be the same as the value of the linear function, half in the middle of the window. So if I'm going to put that as the value here, it's going to register the value a little ways back, a over 2 delayed. Okay, and then as soon as the window starts hitting the peak, you start decreasing, but I claim it's a quadratic decrease, and this is where it's really good to work it out. and it rounds off, and it never gets as high as the peak because there's no average of this function that's actually just concentrates on the peak. The biggest you're going to get is the average across one window width, so it's going to be like up here. Then once you get so that the whole window is on the linear function, so like 2b to 2b plus a, then you're going to start a period of linear decrease, again delayed from the actual linear decrease of the function. Then when the window starts seeing a mixture of 0 and linear, I claim it's going to be quadratic, and then at 3b plus a, it's going to be down to 0. And this is a piecewise differential, it's a differentiable function actually, and it's piecewise smooth. But it actually, at the breaks, and this is a good thing to verify, although it's a little messy with the explicit functions you get, it's really good to verify that at the different breakpoints, there's a lot of different breakpoints, there's like 7 different pieces or something here, that it really actually, the derivatives match up. So we've gone from something that's continuous but not differentiable to an actual differentiable function. Again, a smoothing property. So let's see. What's the next one? I'm reading through all the tedious calculation that I just skipped. Oh yeah. So let's look at a little bit more complicated. It's been very special. We've always used this guy as our convolver so far to get an unweighted moving average. That might be deceptively simple. So let's look at f. Okay. F1. And that is, we're going to define HA of t to be this function. It's going to start out with a certain value, then go down to half that value, and then to 0. This is going to be at a, this is 2a, and then I want the total area to be 1 still. Ooh, that's not dotted. Okay. Total area to be 1. Okay. And then I'm going to convolve that. Oh, I don't really need red anymore, do I? It's kind of garish. And I'm just going to take that and convolve that with a fairly arbitrary function now. We're going to go away from super concrete examples. So there's f of t. Okay. And we're going to take this function. So what's the heights here? If you work it out, this has to be 2 over 3a. And this is 1 over 3a. So we get 2/3, 1/3 add up to 1. Okay. So we're going to convolve this guy with this. And if you've noticed, with the formula for the convolution, f star g of t, there's a little flip with the minus sign. You might wonder why define it that way. And we'll see that it's essential for like the commutativity, lots of stuff. But the t minus tau aspect of it, t minus tau, what that means is that this guy kind of gets flipped and windowed across. So when I look at the value of the convolution, let's say here, now I'll use the red, at some value t, what it's going to do is it's going to superimpose that window. Let's make it kind of small. It's going to superimpose that weighted window flipped across and backwards. And so the value I'm going to create for f star HA of t, right at this t value, is going to be obtained by integrating the f function against this guy. It's going to multiply these two guys together and integrate. And so it's going to weight the most recent stuff more highly. Okay. And we're going to have, let's see, look at my notes here. Let's do this out. Do this out explicitly, just to show how that minus sign works. Make sure we're not confused about that. We'll go back to black though. So f star HA of t is integral minus infinity to infinity. Okay, and so we're going to get f of tau HA of t minus tau d tau. I'm going to cheat. I never tell my students not to do this, but I'm going to modify this in place. Okay, it's going to be 1 over 3a. No, let's say 2 over 3a. I'm going to talk about this part first. That's going to be the rectangular pulse from 0 to a of t minus tau plus 1 over 3a integrate against the rectangular pulse from a to 2a of t minus tau d tau. Okay, and I'm going to modify it in place again. All this does, as usual, this is the one with height 1, not area 1, because I've already normalized it. That just changes it exactly like what we've seen before into the integral from t minus a to t. And that's what I showed you in the picture that I unfortunately had to erase. And then the a to 2a, when t minus tau is between a and 2a, this goes between t minus 2a and t minus a. And that is just going to be, it's 2/3 times 1 over a times this integral. That's just an average value of f on the interval t minus a to t. That's not working very well. Okay, and then plus a 1/3 of 1 over a times this integral. That's the average a little further back in time between t minus 2a and t minus a, rather. Okay, and so it really is exactly the picture I was talking about. Okay, if you want a more continuously weighted average, as it says in the next part, then let's see, so Ka of t, that's going to be a linear function, so 2 over a squared times a minus t, and we'll see why the normalization is like that in a second. And then I'm just going to have that live between 0. That's really the rectangular pulse, actually. I could just call that. I think I modified this from an earlier worksheet, and I forgot I had a notation for that. It's just that guy. Okay, that's just going to be a linear function, slope minus 1, starting at a certain value. It's going to start at 2 over a height, going down. Oh, slope minus 1, but then this changes the slope as well. That's going down and dying at a, and it's just engineered. It's easy to check so that the integral of this guy is 1. I've been consistently using examples where the integral is 1 to really make it look like an average. And it's not that more complicated. Just the very next problem, I think, is talking about how would you think about this if the integral of the tool function in your convolution, the one you're thinking of as a tool, what happens if that integral isn't 1? But let's not worry about that yet. Okay, so again, if I got our function, random function f, I'm going to be flipping, and I want to analyze that at a particular value t. I'm going to be flipping and shifting that window function. And I'm going to be integrating this part of the function, the f, against this guy. And so I'm going to be weighting the near past, the recent past more, and the more and more distant past less. And then after a while, I'm not going to weight the very distant past at all. Okay. And so we're going to get a fairly simple but nice kind of weighted average. Explicitly, we could go back to the example of, let's say, what if we had something that was rather sharp, a step function? Oh, I don't need a t there. Let's take that convolution and evaluate it at t. Again, I'll leave the details of the calculation to the PDF. Okay, so I'll do the black and red style again here. So let's say here's b and here's 1. That's okay, so there's our HB, and then I convolve it. What's going to happen, again, I'm doing a past moving average, so until B, nothing happens. Okay. And then I see this sharp increase, and I see it pretty highly weighted, because the recent past is pretty highly weighted. Now, just like with the other one, it doesn't turn into, it's not a discontinuity anymore. It just starts going up non-differentiably. And then the difference is, because the farther past is weighted less and less and less, when the window finally stops seeing the mixture of 0 and 1, it's really quite gradual. And so right at b plus a, it turns out, it has derivative 0, and then it's continuous and differentiable here. So when I look at that window function, the window function was not differentiable at 0, or not continuous even, and this was continuous here. So we can have a conjecture here about a little more precisely about how the smoothness works, which we want to investigate. When the window function has a discontinuity, and the function we're looking at has a discontinuity. So when both functions have a discontinuity and they're matching up, I get not a discontinuity but a sharp corner, a non-differentiable point. But here, this was continuous, and even though it's interacting with the discontinuity here, it becomes differentiable. And we know that should happen. If we believe, as we're going to prove in a very soon, if we believe that this is symmetrical and this is a commutative relationship, then we could also think of it as convolving Ka with the HB function, and we can conjecture again that convolving with something even discontinuous gives us one more level of differentiability. And so it turns this guy, which was continuous not differentiable, into a point of differentiability of the final answer. Okay, so definitely things to investigate more precisely in the future. That's I think that's a good place to stop. I want to make sure I'm not missing anything from here. Okay, yeah, that's a good place to stop.